When you consider a structure, a real life structure, and if you give it a certain disturbance or some initial conditions. So, what you observe is the structure responds to this disturbance, to this initial condition, and slowly after some time the structure stops vibrating. Now, in our discussions on initial conditions in this course and in the animations that I have shown, once given the disturbance or the initial condition, you have seen that the structure is continuously vibrating, but that is not observed in nature. So, we conclude that there is a mechanism inside these structures, or because of the interaction of the structure with the external world, there is a mechanism which drains out the energy of the structure. So, this mechanism of dissipation of mechanical energy is known as damping, and in this lecture we are going to look at this mechanism, and we are going to model put these damping terms in our models, so that our model looks more realistic. Now, there are various kinds of damping. So, first what I have said, this damping is a mechanism of energy dissipation. Now, what happens to this energy that is dissipated? It gets converted to thermal energy, and this is an irreversible process. This conversion of this mechanical energy to thermal energy in these cases is an irreversible process. Now, most of the damping mechanisms, they work on this, but there is an exception which is known as radiation damping. So, here this is an exception. This damping mechanism, this draining of energy of the structure by radiation damping takes place not by conversion to thermal energy, but by radiation of the energy in form of sound in the fluid medium in which the structure is placed, for example, air or in water or in any other liquid, or sometimes even from the support points of the structure. So, wherever the structure is supported from no support is ideal, that means no support is rigid. So, there will be some flexibility, and continuously energy gets radiated out at the support points. So, we have primarily this energy dissipation by conversion to thermal energy, but there is another mechanism in which it might also be converted or radiated out of the structure. Now, what are the sources of damping? So, the first is known as the internal friction, internal damping or internal friction. So, whenever a structure is vibrating, between the layers of the structure, molecular layers, there is differentials, because of differential straining, these layers they have differential motion, and that dissipates energy. Now, one thing to note is we are considering one dimensional structures. Now, there is no question of any layer in a one dimensional structure, but then we are going to have a phenomenological model based on the rates of stretching, for example, of the structure, the rate of strain. So, strain rate. So, to model internal friction or internal dissipation. The second source of dissipation is external damping. So, the structure might be interacting with an external fluid. So, that provides damping. The third is of course the radiation of energy. So, this is radiation damping. Now, we have we can have distributed damping or concentrated or lumped damping. Now, these internal and external damping because of fluid so internal dissipation and external damping because of fluid, they are distributed damping, while concentrated or lumped damping occurs in this can occur in external damping when we attach a lumped dashpot or damper at a particular point on a structure. So, this typically occurs when we have, let us say, Stockbridge damper in high tension cables. So, that is a concentrated or lumped damping, which is an external damping, and it can happen at connections and joints. So, we can have concentrated or lumped damping at connections and joints, say for example, riveted connections, etc. So, we have these two kinds of damping. Let us begin with distributed damping. So, let us try to model this internal distributed damping first. Here we are going to discuss a phenomenological model for internal damping. So, for example, in a bar, in axial vibration. Now, when we derive the equation of motion of such a bar, we considered this constitutive relation like this. Now, as I mentioned that in order to model internal damping for one dimensional system, we must somehow consider the rate at which this straining is taking place. So, we modify our constitutive relation to include the strain rate. Now, this term this factor is known as the loss factor, and the product of these two terms may be represented as d I, the coefficient of internal damping. So, what we have done is we have introduced in our constitutive relation this additional term, which we will see how this works as internal damping. So, therefore, our stress is given by this. Now, when we use this to derive the equation of motion as we have done before, we consider uniform cross sectional area. So, this term you see is E times del u del x, this gives this term, therefore, this term will give us and along with the boundary conditions, so this is the damping term. So, we have introduced we have obtained this term by introducing this additional strain rate term in our constitutive relation. Now, and similarly with external damping, external distributed damping, we have a term like this, and together with internal and external damping, we have this equation of damped vibration of a bar, of a uniform bar. Now, this can be, this equation may be written in a compact form like this, where this damping operator this is known as the just like this K is known as the stiffness operator. Now, when we so let us first see that these terms that we have considered, these terms, they indeed lead to dissipation of energy, because as yet we have not, we have just introduced these terms, we have not checked whether they really lead to dissipation of energy. So, let us start with this equation of motion, and as we as is the usual way to obtain the energy equation, we multiply this whole equation with the velocity and integrate over the domain of the bar. So, which means what we do is and this must be 0. So, multiply by velocity and integrate over the domain of the bar. Now, these two terms I will integrate by parts with respect to the space. So, what I obtain and this term I can write as can be easily checked. So, this first term can be written like this, and this term now there will be a space derivative of this term, and similarly now, if you use the boundary conditions that we have, then these boundary terms they drop out, because at x equal to 0 the velocity is 0, at x equal to L there is a force free condition. So, this is 0, similarly this is also 0. So, what we are left with is this integral. Here again I can write this term. So, you see I can write this also as a time derivative . The time derivative I have taken it out, and I will take the other terms on the right hand side. So, you see on the right hand side we have an integral which is this integral is always positive provided dE is positive. So, if this integral is positive, if this dE is positive and eta is positive, then this integral is positive. Here there is a negative sign. So, the right hand side is always negative. So, which means this is always less than 0 provided dE is greater than 0 and eta is also greater than 0. Now, this is nothing but the total mechanical energy of the bar. So, this is the kinetic energy, this is the potential energy, we have already seen these terms. So, the rate of change of energy is always negative, which means energy always dissipates or drains out of the system. So, the mechanical energy is always dissipated by terms, by these damping terms that we have considered. So, these two terms. So, this shows how the energy dissipates with time. Now, if you if you integrate, so suppose you have forcing, So, in that case this energy equation, so I will write as d E dt and suppose in addition you have forcing. So, this additional term would come because of external forcing. Now, if you suppose this forcing is something like this harmonic forcing that we have considered. So, we know already, we have discussed this, that there is a steady state solution, and because of this damping now, as we have seen here, all the energy of initial disturbance. So, suppose you have an initial disturbance, then that energy must dissipate or drain out of the system. So, what we are left with is the steady state solution. So, any initial condition, any disturbance created because of an initial condition must dissipate out, as we know from here. So, if we have the harmonic forcing, for example, what will remain at sufficiently large times is the particular solution, which is generated only because of this external forcing. So, you can estimate the so from here you can estimate what happens at steady state. So, at steady state the motion is periodic, therefore, if I integrate this energy equation over one period, the change of energy must be 0. So, therefore, I can write here I am assuming that this forcing is periodic or harmonic. Now, so at steady state, if there is a steady state solution, then at steady state the energy change over one period must be 0. Therefore, this is what we obtain. So, what this says is the energy provided by the forcing over one cycle is equal to the energy dissipated by the damping terms over one cycle. So, from here you can estimate many things. For example, you can estimate the damping. Suppose you give a harmonic input and you record the amount of energy that you are supplying over one period, then you know how much energy is being dissipated. So, you calculate this term and that will give you an estimate of energy dissipated by the damping mechanism in the system. So, what we have concluded is that any initial condition or any initial disturbance must die out because of these damping terms, and what remains is the steady state solution, and that can be used to estimate the energy that is dissipated, and that can be used to model the internal dissipation, as well as you can estimate the amplitude of motion in certain cases. Now, let us once again look at this damped system with certain boundary conditions. We so this along with certain boundary conditions, let us try to find out the solution, or let us discretize this system as we have done before using the modal expansion. So, these are the eigenfunctions of the undamped eigenvalue problem. So, when you substitute in here, then and finally take inner product with the jth eigenfunction, what we obtain these steps we have done many times before. So, I have directly written the jth the coefficient of the jth term in the solution. So, I can carry this out for all j and get all the equations governing the jth the modal coordinates. Here this d j k, this matrix, is given by this integral. Now, in general there is no guarantee that d j k is diagonal. Now, if this is not diagonal, then all the modes are coupled. So, all the modes are coupled through this damping term. Now, under very special situations, this damping matrix, this will be a completely diagonal matrix. So, let us look at that condition. So, that condition follows very easily from here, if d u k is some d k times mu x times u k. So, for all eigenfunctions, if the operator operating on this eigenfunction gives this, in other words, u k is also an eigenfunction of the operator d, the damping operator, then the damping matrix is completely diagonal, as you can see from here. So, one choice of this damping operator for which this happens is when the damping operator is a linear combination of the inertia operator and the stiffness operator. Such a damping operator is called the classical or proportional damping operator. So, classical or proportional damping, we say that a system is classically or proportionally damped when the damping is linear combination of the inertia and the stiffness operators. So, in that case our equations completely decouple, and so we have completely decoupled system of differential equations when the damping operator is classical or proportional. Now, so we have looked at internal and external damping. Now, let us delineate the roles of these internal and external damping terms. So, let us see how they are actually a little different. So, for this let us consider. So, we are going to look at the difference in roles of this internal and external damping. So, to understand this, let us consider this simple example of a fixed bar in axial vibration. So, the equation of motion is this. The boundary conditions are given by this. So, therefore, I can expand as you know that these are the eigenfunctions of this fixed bar. So, when you substitute this expansion and take inner product, so we substitute this expansion in the solution and take inner product with sin k pi x over L, and that filters out the kth coefficient in the expansion. So, what we are going to get So, this term is for the external damping, this term is for the internal. So, this external, this is the internal damping, and so this is what we are going to get. Now, let us look at this equation one by one. So, suppose there is no internal damping. In that case, so when we have only external damping, I can write this as which can be written as and if you compare, then zeta k can be written as this. So, you see that this k appears in the denominator of this damping factor. So, which means that for high values of k, this damping factor actually is very low, which tells us that external damping is not inefficient in damping out higher modes. So, higher modes are damped less compared to the lower modes. We will look at the reason for this. Now, let us consider the internal damping case. So, in that case I can write and once again, if you represent this term as 2 zeta k omega k, then now you see that k appears in the numerator. Therefore, for higher modes, higher values of k, zeta k is high, goes higher. So, which means higher modes have better damping because of internal dissipation. So, internal damping is more effective for higher modes, while external damping is more effective for lower modes. So, external damping is effective for lower modes. While internal damping is effective for higher modes. Now, to understand this, you have to look at the expression of say for example, the internal damping. So, we have seen already that this internal damping, the way we have introduced, so it is strain rate, dependent on strain rate. Now, as you go to higher modes and if you consider the solution, then del u del x, so rate of change of del u del x, rate of change of del u del x with time. So, if you see this solution is, say for example, for this bar, so you have terms in the expansion of u like this. So, del u del x, so so higher the value of k, higher is the contribution from this strain term at the strain rate term. So, for this reason, higher the mode, higher will be the effectiveness of the internal damping. On the other hand, if you consider this external damping, if you look at say for example, the first mode. So, the first mode of the bar or the string looks like this, the second mode looks like this, the third mode looks like this. So, higher the mode, more will be the nodes, and therefore, the effective motion of the system in the ambient fluid will be lesser and lesser. So, the effective damping because of external damping reduces as you go to higher modes. Now, let us look at discrete damping. Now, as I have already mentioned, this discrete damping occurs when we attach, for example, an external dashpot to a continuous system at a particular point. Say for example, stock bridge damper is typically used in high tension cables. So, that is attached to a particular point on the cable, and that damps the vibrational energy of the high tension cables. So, this is a discrete damping or a lumped damping. Other than that, you can have lump damping when you have connections or joints. Say for example, you have riveted connections between two structural elements. In that case, damping is localized at the connection or at the joint. So, for such cases, what you have is the discrete damping. So, let us look at an example. So, this is a bar in axial motion, and here we have a dash pot attached to this end of the bar. So, I can write the boundary conditions of this problem. So, this is a fixed end and at this end I have the force because of this damper. The equation of motion is like this. Let us search a solution of the form like this. So, we have a discrete damper at this end, and we have introduced this damping not in the equation, but in the boundary condition, which we can always do. Now, once you have once you substitute this solution form in the equation of motion, we obtain an eigenvalue problem you obtain this eigenvalue problem, and the solution of this eigenvalue problem can be written in this form. And when we use the boundary conditions, so these two boundary conditions can be written in this form, where gamma, this gamma is S times L over C, and this A here, this small c is of course the speed of axial waves in the bar. So, we have to solve this system. The solution for non-trivial solutions of B and C, so for non-trivial solutions of B and C, the determinant of this matrix must be 0, which leads us to as you can very easily find out that this is the equation which is the characteristic equation. And which can be solved for gamma when A is not equal to 1. When A is equals to 1, there is so this can be solved when A is not equal to 1. if A is equals to 1, which implies that the damping. So, the adjustable parameter is the damping. There are no eigenvalues. There are no eigenvalues for this problem when the damping is tuned to this value. Now, so no eigenvalues would imply there are no solutions. Now, but then we have considered solutions of this very special form. So, there are no solutions of this very special form, but then there are solutions which we have to understand in terms of wave propagation. Now, that we will keep for a later discussion. Right now, let us solve when A is not equal to 1, and for solving that we can consider gamma to be a complex number of this form, and then so alpha plus I beta. So, alpha can be easily solved as log natural of and beta is indexed now the phase So, there are infinitely many values of beta which are now indexed with k, and for various ranges of values of A we have these solutions, and you can check if you put D as 0, then you can get the eigen values of a fixed free bar. And if you put D as infinity, then it is a fixed bar. And that can be checked from these solutions that of gamma that we have obtained. Now, here in this slide I have plotted the variation of alpha and beta. So, the solutions of gamma, the real part and the imaginary part, as A varies. So, when A is 0, we have a solution here. So, A will be 0 when the damping is 0, which means it is a fixed free bar, while A is infinity when D is infinity. So, this is a fixed bar, and when A goes to 1, this goes to infinity, as we have already seen, and when A so this is the locus of the solution as A varies. So, as you can see that all modes have the same decay rate, as alpha does not change or does not depend on k. So, all modes will have the same decay rate, and there is a jump from this value to this value as A crosses 1. So, we have considered one case of a bar with boundary damping. Let us look at another example of a string. With a concentrated damper or a lumped damper at x equal to A. So, in this case you can write down the equation in this form, and if you use the modal expansion, substitute in the equation and take inner product with the jth eigenfunction, you obtain this. Now, if you consider that this j times A over L is not an integer. So, if you can adjust this A such that this is not an integer for all j, then you will find that all modes are damped, whereas if this does not happen, then some of the modes will not be damped. So, for this situation, when this is not an integer, what we have is known as pervasive damping. So, when the damping is pervasive, all modes will be damped, whereas if you put this damper at the middle of the string, you will find that the second mode is never damped. So, the second mode, the fourth mode, these modes will not be damped. So, the damping is then non-pervasive. So, in today's lecture what we have studied is this, we have introduced the damping and we have seen two forms of damping, internal and external. We have studied distributed damping and lumped or concentrated damping, and we have delineated the effects of internal and external damping. So, with that we conclude this lecture.